Here we have again, we have two objects, mass 1 and mass 2. So what we have is like a table, and on the edge of this table, we have a pulley. And so that's that's my depiction of a pulley, massless, frictionless pulley, and we have a massless, inextensible rope connecting mass 1 and mass 2. And so mass 1 is 9 kilograms and mass 2 is 3 kilograms. So my question is there going to be acceleration to this system? Take a moment to think about it. And yeah, there will be. So without any friction between mass 1 and the block, there's nothing to oppose the weight of mass 2 pulling this down, pulling down that tension, and pulling on this, right? Because Newton's second law is a net force is equal to the mass times acceleration. There's no force opposing this force pulling down here because there's no friction. If there was friction, that would be a different situation. So this one will accelerate down, and this one will accelerate to the right. Both of them with both of them with acceleration a. It's the same acceleration. The rope will not stretch. And so for this one, we want to know what is the acceleration and what is the tension in the rope. Which, by the way, the tension here is equal to the tension here on the top of that, the top part of that rope. Let's draw some free body diagrams for mass 1 and for mass 2. We'll start with mass 2. That's a little bit easier. It's going to accelerate down. Well, regardless, it has a m2g gravitational force on it. The string is, or the rope is pulling up with a force Ft. Excuse me. And the acceleration goes down like that. Okay. Mass 1 also has, in this case, a greater m1g force. It has an equal amount of force, the Fn, normal force on it, and it's being pulled to the right with a force Ft. I'm going to try to draw that the same length as that Ft there. Same amount of force there. And of course, this one is accelerating in this direction. We're going to write our equations of motion. The sum, sorry about that, excuse me. Sum of all forces on mass 1 equals m1a. And the sum of all forces here equals m2a. And so again, we're only concerned with forces that have anything to do with that acceleration. In this case, these are the vertical forces. And in this case, this is just the horizontal force here. So that is Ft equals m1a. Over here, whoops, that should have been there. It's m2g and Ft. m2g must go first. It's accelerating in that direction. And Ft goes here, equals m2a. Now, if we're going to solve for acceleration, in this case, we need to know both of these numbers if we're going to solve for acceleration, but we don't know Ft. So we're stuck. And over here, if we're going to solve for acceleration, we need to know m2, we need to know Ft, and well, m2 again, which we know m2, but we don't know Ft. So too many unknown variables. But it's not a problem for us. We're going to figure it out. We're going to substitute just like we did in the other videos. This one's even easier because we have an expression for Ft, and so we can substitute m1a into this expression. Now you don't have to show this on a quiz, but I'm just showing this for the purpose of notes, that we're going to take m2g minus m1a equals m2a. want to solve for A, so I want to get all my A expressions on one side of the equation, so kill two birds with one stone and get rid of that negative as well. We'll add M1A to both sides. And we want to get A by itself, but we should factor out an A from these expressions. So this is A on the outside of M1 plus M2. And to isolate A, we'll just divide by M1 plus M2. Equals A. Mass 2 is 3. Mass 1 is 9. So 3 times 10 is 30. 9 plus 3 is 12. And so 30 over 12 actually looks like 2.5. Didn't have my calculator handy, so I'll get that going here. Excuse me. Cool, that's the acceleration. This one going down, this one going off to the right. Now we're going to solve for ft. It's very easy now. Ft is over here. We'll put in mass 1, which should have been the 9. The acceleration is 2.5. And 9 times 2, 18. 18 plus 4.5, 22.5. Should really calculate just to be sure. Cool. 22.5 is the tension force. Now, these objects are moving with the same acceleration. They're moving kind of together. So we can also look at this as a system. We imagine that those two masses are together. So the sum of all forces on that system is equal to M1 plus M2A. And we have to think about what forces are causing the system to accelerate, and are there any opposing forces to that acceleration for the system? And if you think about it, what's making this system accelerate is the M2G. The gravitational forces M2 is what's pulling this thing through. Now, there's not really a force that opposes. I mean, there's not. Yeah, we have a tension force that's pulling up on this, but we also have a tension force that's pulling to the right on M1. So those are kind of canceling there. This is the only force contributing to that acceleration. And so to get this isolated, to get A isolated is M1 plus M2. And of course, that's the same expression that we have there. So we're going to get the same result. Cool. Trying to see if there's anything else we need to say here. Once again, we haven't asked for it. What is Fn? It's trivial here. Fn is equal to m1g. There's no acceleration for mass 1 vertically. Now, actually, there will be something I'll say. If there was friction on this block, let's say there was a friction force on this block, that's probably something I would give you. I'd tell you the number. I'd say maybe it's 3 newtons or something like that. 3 newtons of force. So if there is friction on that block, then we would add a friction force here. And our statement, this one, would instead have to say Ft minus Ff equals M1A. And then we're off and going. And I should have made that a little bit smaller, because it will accelerate to the right. Well, it all depends, right? If the friction force is equal to Ft, well, anyway, let's not make it complicated. let's just say we had a little bit of friction force here. We would put it there in the equation. Now for the system, if there was friction, we would have to say m2g minus ff, because that ff would be a force that is affecting that acceleration. It would give us less acceleration. So yeah, your equation over here would look something like this. Yeah, something like that, or exactly that. Anyway, and I'd probably give you that number if we were meant to solve. Okay. Last one here is important for one of your homework questions. You have an elevator that's being accelerated upward. There's two masses in here. Mass 1 sits at the bottom of the elevator. Mass 2 sits on top of it with masses 5 and 3 respectively. The acceleration of the elevator and of mass 1 and of mass 2 is all 1.2 meters per second squared. And so first what we'll do is we will draw free body diagrams for mass 1 and mass 2. And I didn't put any questions here. We really just want to do this as an exercise to see how we draw the free body diagrams. And you can pause the video and try it on your own first. You'll learn this way. You'll learn more, I think, this way by trying it out and seeing what you get and comparing it with what I'm going to write here. Mass 1 is greater than mass 2, so we would draw it a little bit longer. The gravitational force, and then m2g. So we can start with the forces we definitely know are on each object. And I'm going to switch over to mass 2 and just focus on this one. Mass 2 has a gravitational force, but it is accelerating upward from a force coming from mass 1 is pushing on mass 2. And that should be greater because it is accelerating up, so this force must be greater. And right here we have a choice. You have a choice of what to call this. This could be a normal force, which it is, from mass 1. Or you can say it's a force that mass 1 puts on mass 2, and I typically write that as F12. So I'll kind of leave it to you what you want to choose. And we're going to have to actually modify one of these in just a minute here. But that's it. Mass 2 just has gravitational, and mass 1 is pushing it up. There is no tension force in this problem. The tension is affecting the elevator, which is not part of our free body diagrams. Our free body diagrams are just those masses there. Now let's talk about mass 1. Mass 1 is getting an upward force from the bottom of the elevator. I'll draw it like that. And let's draw it a little bit longer. Erases. Because it is accelerating up after all. And we can't have both of these say Fn because they're not the same amount of normal force. So I would say, let's call this Fn1, and so this one I would call Fn2 if we're going to call it that way. Okay. But that's not all. There's actually another force we need to account for here on mass 1. So let's think about this. Mass 1 has a gravitational force. The elevator is pushing it back up, but M2 is putting a downward force on mass 1. And we actually already know what that force is. So this force here is the force that 1 puts on 2, which should be equal but opposite of a force on mass 1. And so you can call this one of two things. You can say Fn2 because that's the same amount of force. But if you called it F12 over here, you should probably call this one F21. The force that mass 2 puts on mass 1. And you just have to make a statement saying that F2 on 1 is equal to F1 on 2. It's the same equal but opposite force on. Newton's third law, you get the idea. Mass 1 puts a force on mass 2 going up. Mass 2 puts a force on mass 1 going down in equal magnitude, opposite direction. Cool. And so these are done here. Did we? Yeah. Everything we wrote here looks good. So if there are different magnitudes, just know that they can't be labeled the same thing. So Fn1 and Fn2 are different magnitudes. That's why we had to call them different things. And that should help you with your homework, just setting up the free body diagrams. Here, one of the questions I'm sure I would ask you was, what is that force F12? Or in other words, what is the force F21 on the object? And that is it.